Have you ever looked out the window of a commercial airliner, staring into a complete whiteout of clouds, and wondered how on earth does this aircraft, flying at 30,000 feet at hundreds of miles per hour, know its exact distance to a runway that's completely hidden miles away? It's a massive, real-world navigation problem, but modern aviation has a brilliantly elegant, invisible solution pulsing through the air right this very second.
Welcome to this explainer. I am so thrilled you're here, because today we are going to unpack the hidden infrastructure that makes flying safe, precise, and highly calculated. We're decoding DME, which stands for Distance Measuring Equipment.
Okay, let's dive right into this. Here's our flight plan. First, the basics of DME, then primary versus secondary radar. Next, the anatomy of the system, followed by how distance is calculated, overcoming signal traffic, and finally, system limitations and accuracy.
All right, Section 1, the basics of DME, finding your way in the sky. So let's establish the fundamental requirement here. Knowing an aircraft's position is absolute ground zero for air navigation. To pinpoint that, you need two things, bearing and distance. Distance measuring equipment, or DME, handles that second part. It's an en route navigation system that literally gives pilots their physical distance to a known ground transponder, always expressed in nautical miles. But it doesn't just stop at distance. If the aircraft has the right computer on board, this steady stream of data can be used to instantly calculate ground speed and the exact time needed to reach the station. It's like having a hyper-accurate stopwatch and speedometer rolled into one.
Moving to Section 2, primary versus secondary radar, the echo analogy. To truly appreciate DME, we kind of need to understand how it fits into the broader world of radar. Let's compare these two core concepts. Primary radar is essentially passive. A short pulse is transmitted out, it bounces off an object, and the system measures the time it takes for that reflection to come back. Think of it like shouting into a canyon and just listening for your own echo. Secondary radar, on the other hand, is completely active. Interrogation pulses are sent out, and when they hit the target, they pass through a preset electronic gate that triggers a deliberate active reply back to the source. So instead of just listening for a passive echo, secondary radar is like shouting a specific code word to a friend across the canyon, and they actively shout a code word back. DME is a form of this secondary active radar.
Section 3, anatomy of the system, the three core components.
Let's build a quick mental map of the actual physical hardware we're dealing with. Up in the sky, installed right on the aircraft itself, we have the interrogating equipment, aptly named the interrogator. Down on the earth below, serving as the target, we have the transponder, which you'll often hear referred to as the ground beacon. These two pieces of hardware are basically locked in a continuous, invisible conversation. Now, what's really interesting here is how this bridges the gap between what's happening outside the plane and what the pilot actually sees inside. There's this massive invisible signal exchange happening between the plane and the ground on ultra-high frequencies, specifically buzzing between 962 and 1213 megahertz. But obviously, pilots don't see radio waves. Instead, this highly complex UHF exchange is instantly translated into the cockpit navigation display unit, giving the crew clean, readable data they can absolutely trust. Which brings us to Section 4, how distance is calculated, the microsecond math. I am so excited for this part because it's the absolute climax of how this whole thing operates. We're going to peek under the hood at the physics that makes it work. I want you to burn this number into your mind. 50, specifically 50 microseconds. When the ground transmitter receives a signal from an aircraft, it deliberately waits exactly 50 microseconds before transmitting its reply. This intentional pause is literally the linchpin of the whole operation. Let's look at why. Here is exactly how the magic happens, step by step. Step 1, the airborne transceiver transmits a pair of pulses. Step 2, the ground transmitter catches them, and, as we just learned, it holds onto them for exactly 50 microseconds. Step 3, the ground station replies back to the aircraft with paired pulses, but on a totally different frequency so signals don't get crossed. Step 4, this is where the onboard computer goes to work. The aircraft measures the total round-trip time, but because it knows the ground station deliberately paused for 50 microseconds, it subtracts that 50 microseconds from the total. What's left is purely the travel time of the signal. It multiplies that time by the speed of light, and finally divides by 2, since the signal had to go there and back. It is a brilliant speed-of-light calculation happening continuously while you're just sitting there sipping coffee in the cabin. Now, there is a crucial caveat here about what kind of distance we're actually measuring. DME provides what is called slant range. This is the direct line-of-sight distance from the aircraft high up in the sky straight down to the ground station. It is not the flat, horizontal ground distance you'd plot on a paper map.
This means the altitude of the aircraft plays a major role. Think of it as the hypotenuse of a triangle. Even if an airplane is flying perfectly above the ground station at an altitude of 6,000 feet, the DME will read a distance of 1 nautical mile, because that slant range is never zero as long as the plane is up in the air.
All right, Section 5. Overcoming signal traffic. Finding your own voice.
This introduces a fascinating logistical puzzle. We know how one plane talks to the ground station, but what happens when the sky is completely crowded? 100. A single ground DME system has the capacity to handle interrogation from up to 100 different aircraft simultaneously without breaking a sweat. But if dozens of planes are all pinging the exact same station at once, how does a single aircraft know which replies are its own and which are meant for the plane 3 miles away?
The answer is a really clever concept called jitter. When an aircraft sends out its signals, it doesn't send them at a perfectly steady, predictable rhythm. Instead, it transmits them at a randomly varied pulse repetition frequency, or PRF. This random sequence is the jitter. The interrogator on board essentially remembers its own unique jitter pattern. When the ground station replies, it echoes back at that exact same varied rhythm. The airborne receiver then compares all incoming signals against its stored memory. If the jitter matches, the plane knows, that's my echo, and calculates the distance. Plus, to keep the airways clear of confusing reflections, the ground station uses a 60 microsecond dead time after it replies, meaning it momentarily ignores everything else so false reflections don't clog up the system. It's incredibly elegant.
Finally, Section 6, System Limitations and Accuracy, Trusting the Instruments. We've talked about microsecond math and randomized frequencies, but how do we ensure this is actually safe to rely on when hundreds of lives are literally up in the air? Well, this brilliantly illustrates just how robust this technology is. Look at the official International Civil Aviation Organization, or ICAO, standard. The allowable error for DME is 0.5 nautical miles, or 3% of the distance. That is the official baseline. But look at the real-world performance. During tests conducted on Canadian DME stations, the actual tested error was less than 30 meters. The system isn't just meeting the standards, it is vastly outperforming them, giving pilots jaw-dropping accuracy that they can implicitly trust.
But of course, trust requires a failsafe. Ground stations aren't just left alone out in a field to transmit blindly. They are equipped with highly strict integrity monitors that continuously watch the system's own performance. If these monitors detect that the crucial 50 microsecond delay is slipping, or if the power output levels fall out of tolerance, they don't just send a gentle warning. They instantly shut the entire system down. Because in aviation, no information is vastly safer than incorrect information. The system literally protects its own integrity by shutting off before it can ever lie to a pilot.
So the next time you're sitting in a window seat, looking out at an endless sea of clouds, I want you to think about that microsecond math happening invisibly right outside the fuselage. It begs a pretty wonderful question, doesn't it? If invisible pulses bouncing at the speed of light can guide us blindly to a runway with 30-meter accuracy, what other incredible, invisible infrastructure are you flying through right now? Thank you so much for joining me for this explainer. Keep learning, and I'll see you on the next one.